Good morning, everyone. Welcome to Chemistry with Professor John. All right, hope you have a good day today. We are moving on to alkyl, and this is a good, quick review and homework. Okay, let's get right into it. All right. Alkynes. All right, guys. We spent a lot of time on alkene because we wanted to do a good job. And when you set that good foundations, alkynes, it's just another easy one, right? Same logics. Okay, alkyne is the one with a triple bond. So triple bond means we have to give up 4 hydrogens. Every time you've got a carbon-carbon double bond, a carbon-carbon bond, to make every 2 hydrogen you give up, you make an extra bond, right? And that's a pi bond. The first bond is a sigma bond, and then the 2 bond that we form, it will be 2 pi bonds. And there you go. We got a triple bond. A triple bond has 2 degree of unsaturations. 2 pi. Okay, a pi bond is a degree of unsaturation. Also, a ring structure is a degree of unsaturation, meaning reduced number of hydrogens. 1 degree of unsaturation equal to 2 hydrogens. So this one equal to 4 hydrogens, right? All right, everyone, let's start with naming. This is the fun part, right? Again, similar logic. We have to number the carbon on the end that's closer to the triple bond. Okay, here we go. 1, 2, 3. You got the first carbon of the triple bond. Now the branch is not as important. So if you go on the left side, 1, 2, 3, you got a methyl, but that's not as important as the triple bond. So therefore, we got a 6-methyl 3-octi. Oct means 8, total of 8 carbon. We got first carbon of the triple bond is on carbon number 3. All right, what if we got 2 different functional groups? One is a double bond and one is a triple bond. Now, if there's a tie, we're going to go with the double bond first. So therefore, we're going to call this a 1-heptene 6-I. I mean alkyne. We still have to name I last. 6 is the first carbon of the triple bond. Now you can also do hep1ene 6I. Okay, that's the new way. Now if we got a alkyne that's number 1, then we got to go with that one first. So that's why 1, and then we got a 7 alkene, right? So we have 4-methyl, 7-nonene, 1I. So you always end with the triple bond as a parent. Okay, or the new one. So now, your turn. How do you name the following? Okay, well, this one is symmetrical. It looks symmetrical molecules to me, so it doesn't matter you go from left to right or right to left. End up with the same numbering, right? 1, 2, 3, 4, 5, 6. So we got a methyl. So it looked like we have a 3. If we go from the right to left, it's the same thing. 1, 2, 3, 4, 5. Yep. So it's always going to be a 2,5 dimethyl 3 hexi or hex 3I. This one I would do 1 right here if you guys agree with me. 2, 3, 4, and you got a methyl on top and bottom. So we got 3,3-dimethyl, 1-butyl. Looking good, right? Okay, this one, if we do from the left, it's 1, 2, 3, 4. But we go from the right is 1, 2, 3. That's better. 4, 5, 6, 7. And we got a lot of branches. That will be a 2, 5, another 5. Trimethyl. And this is going to be a 3 heptide. Okay, here we got 2 double bond and a triple bond. So we're going to go 1, 2, 3, 4, 5, 6, 7. Hopefully I got everything there. Now, this one, we got a 3, 5, right? So we got a 3, 5, a 7, so that's a hep. 3, 5 diene, and it's going to be a 1I. That's one way to do it. Or we can do 3, 5 heptadiene, 1I, right? Okay, guys. Those are reactions, and we have more in the books, okay? And the homework. Now, in terms of reactions, to make the first 2 reactions are to make alkyl. How do we synthesize, right? And you can do 2 eliminations. So if you have an alkene, you can turn that into the visional, mean right next to each other, dibromide or dichloride. So every time you eliminate a hydrogen and a bromine, you got a double bond. And if you eliminate the other one, the other pair, you got a second double bond with a strong base. So this one will be double elimination E2. Very simple. You guys see it? Beautiful, right? The second one. Now, you can also start out with an alkene, and you use also a strong base. You need 2 moles of sodium amide, sodium plus, amide minus. Amide take the hydrogen, make the triple bond, kick the Cl out. Pretty much, same principle, right? E2. Okay, now we got alkyl. What kind of reaction we can do? Okay, very similar to alkene. You can add. You add HBr. Br is going to go into the more substituted carbon or the inside carbon. Hydrogen will go to the outside. Now here's a nice thing. You can add the second moles of HBr, and it's going to happen the same. Both Br go into the more substituted carbon, and then both hydrogen could go to the outside, right? That's a 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you can do like that. Br. That's it. 1, 2, 3, 4, 5, 6. That's the same. HCl, it's the same, In this case, it doesn't matter. Symmetrical molecules. 2 chlorine atom go to the same carbon, and 2 hydrogen go to the same carbon. Very nice. Well, however, the first one, you notice that when you do the first one, they go opposite. But when you they add it opposite. But when you do the easy nomenclature, then they become It may look like a trans, but it's actually a cis because chlorine has higher priority compared to ethyl because it's atomic number chlorine 17. Okay, now comparing the adding, right? Adding HX to alkene versus alkyne, and now you can see they come in. Well, because this one, I mean, it looked like they come in on the same side, but it doesn't matter because it's single bond free rotation. But this one, they do come in on the opposite side. That doesn't mean it's a trans though. Okay. So just to give you an idea how HBr or HCl added to the triple bond, just one. Okay, the first additions. Now bromine is going to be very straightforward because you add one bromine to each carbon. So you got the two bromine coming in. Notice that they are trans, and that make these molecules also trans. And when you add the second bromine, then they all filled up, so it doesn't matter anymore. Okay, so here if you add two, then it's going to be 1, 2, 3, 4, 5. So I'm going to go ahead and do line formula, so it's a lot easier, right? So you got 2Cl will go in the same carbon, and wait, and then you got 2Cl here, so you got a total of 4, right? Okay, so it's really nice. It's all single bond, so we good. This one, we got C and CH, Cl2. Oh, actually, wait a minute, not too fast. This one is CH, and then we got HBr, but we only do one, so we still got a double bond, right? We still got a double bond. So this is Markovnikov. So the Br is gonna go in here, and then the hydrogen is gonna go out there. Here's another Markovnikov. You got the H gonna go there, and the Br is gonna go there. So you got 1, 2, 3, 4, 5, 6, 7. So 2, okay, and then 3 got the Br, and you still have a double bond. Okay, all right. Moving on, hydration, adding of water. Now this one is cool. Adding water. Instead of using mercury acetate, we can use mercury sulfate. It's Markovnikov. So when you add water, the OH go into the more substituted carbon, and you still have a double bond. So what happened is this hydrogen get transferred to the carbon, and then the OH bond got converted to a double bond O. So we end up with 2 hydrogen added to the outside carbon, okay, and oxygen added to the inside carbon. So we got a ketone, like double bond O. I mean 2 hydrogens because water is H2O. You guys can see, and then the oxygens there end up there. Okay, now for internal alkyne, you got either one. Either you got two different carbons, so you got a mixture of the two ketones. If you got a terminal, obviously we got oxygens gonna be right there, and the 2 hydrogens can be right there, right? Pretty cool. take a look real quick of the mechanism. You can see mercury sulfate help out to to form the cation, and then water comes in and eliminate the hydrogens, and you got the enol, and then rearrange into it's called actually tautomerization into ketone or aldehyde. Okay, now I'll let you guys practice this, and then we'll continue in the next video. We'll finish this up in the second video for alkyne. Well, thank you everyone. All right, I'll see you guys soon in the next video.